Hello again. In this video, we are going to look at how to apply the numerical integration method for calculating the element quantity, that is element stiffness matrix, element mass matrix, and element force vector for 1D two-noded element. Okay. So we use the 1D two-noded element, and for this element we know the basis functions. So we can derive them in the physical coordinate system x in terms of the nodal coordinates x1 and x2, and then we can integrate the corresponding expressions for the element stiffness matrix, element mass matrix, and element force vector. Okay. And these are the expressions in terms of the parameter mu and the element length he, and here rho is like density and f is the specified source term. So let's take an example of an element with coordinates 0.2 and 0.3. Okay, so the first node is at 0.2, the second node is at 0.3, and we can calculate the length of the element, which is x2 minus x1, so 0.1 units. And let us take these parameters for the purpose of calculations. Mu is 2.5, rho is 12, and f is 2. So if we substitute these parameters into these expressions, we get the element stiffness matrix, mass matrix, and force vector. Mu is 2.5, h is 0.1, so 25. So 25 minus 25 minus 25, 25. And rho is 12, h is 0.1, so 1 and 12 by 6, 2 multiplied by 0.1, 0.2, so 0.2 times 2, 0.4, and here 0.4, and 0.2 times 1, 0.2, 0.2. F is 2, 2 by 2, 1, h is 0.1, so 0.1, 0.1. Okay. So we use this as our references for verifying the calculations using the Gauss quadrature or numerical integration. Now, before we go into the actual calculations of the stiffness matrices and mass matrices and the force vector, first let's understand what is numerical integration. What do we do? How do we evaluate the integrals using this numerical integration procedure? So, in the numerical integration procedure, let's say we have an integral I. Okay, so this integral is the integral of the function f, which is a function of xi. Okay, xi is the parameter. Okay, and xi varies from -1 to +1. Okay. So in this numerical integration, we always have the limits. Okay, for this 1D problem, the limits are always from -1 to +1. Okay, there are some valid reasons for choosing these limits. We can as well derive the numerical integration schemes for different limits, but this is what we use. This is the standard that we use. Okay, so in the xy coordinate system, the integral is from -1 to +1, and we evaluate this function f. That is, we evaluate the integral of this function f from with limits from -1 to +1. If the function is simple enough, we can use analytical techniques. We can find the integral and then apply the limits. But most of the time in complex computational science, computational engineering problems, the integrals are not so straightforward, so we cannot evaluate them using analytical methods. So that is why we use numerical integration. Okay. So how? So in the numerical integration, we use summation. Okay. We sum over a number of Gauss points. Okay, from 1 to a number of Gauss points, and at each Gauss point we evaluate the function f at that Gauss point and multiply it with the weight. So once we do this for all the Gauss points, we sum them. We have a variety of streams in terms of the number of draws points. Okay, so the draws points are denoted by the squares. So they spread all over the domain from -1 to +1. Depending upon the point number of points that we use, we have like 1 point quadrature rule. In this 1 point rule, there is only one draws point, and which is at the center. So that is xi equal to 0. Okay, the xi coordinate is 0, and the weight omega is 2. Okay, and using this 1 point quadrature rule, we can integrate polynomials in xi up to of degree 1. Okay, if we have a linear polynomial, then we need only 1 point rule. 1 point rule is sufficient. We can use more, but it is just waste of computing resources. We always use the minimum number of draws points. And in the 2 point rule, we have 2 points which are placed symmetrically on either side of the center. So if it is plus, then this will be minus, like this. So we have 2 points. So placed at -1/√3 and +1/√3. For these 2 points, the weights are 1 and 1. And using 2 points, we can integrate up to like third degree polynomials. So we can extend these rules. We can have we can develop a 10-point rule, 20-point rule, and so on, depending upon our requirements. And okay, so draws quadrature with n points exactly integrates polynomials of up to degree n-1. So if you have 2 points, we can integrate up to degree 3. Okay, 2n-1 is like 2 times 2 minus 1, so 4 minus 1, 3. And we can reverse this calculation, and we can find out how many points we need if you have a polynomial of degree n. Okay, so if you have a cubic polynomial, so 3 plus 1 by 2, so 4 by 2, 2. We need minimum 2 points. If you have a quintic polynomial, so 5 plus 1 by 2, 6 by 2, 3 points. Okay, so this is our, let's look at some example. Okay, let's take these two integrals and let's evaluate. For our reference, I have calculated them, and these are the values. Okay, so we use them for our verification. Let's see. For the purpose of evaluation, so what I have done, I have prepared a function which gives us the coordinate values and the weight values for a given input of number of points. Okay, so here I have a function get draws points. For a given ngp, number of draws points, it will give the draws point coordinates and the corresponding weights. Okay, so let's start with one draws point. So from here we get the coordinates of the draws point and the weights. So what do we need? We need a loop. So gp equal to 1 to ngp. Okay, so we close the loop. Now before we start the loop, what do we need to do? We need to initialize the integral to 0, because we are doing summation, so we keep on adding to the integral as we loop over the draws point. So we first need to initialize the integral value to 0. This is important, otherwise you will get rubbish. Okay, and then okay, so we get the coordinate xi. Okay, so we start it from our arrays corresponding to this draws point, and then we extract our weight corresponding to the draws point. Okay, now we know that this 1 minus 2 xi is our function f. Okay, and at this value of xi corresponding to the current draws point, we evaluate f. F is 1.2 minus 2 xi. Sorry, 1 minus 2 xi. Okay, that is our f. So we calculate I is our integral. So and another important thing to remember is that we keep adding to I. So I equal to I plus. And then, so to this, what we need, what do we do? Okay, F multiplied by the corresponding weight. Okay, so F multiplied by the weight. Okay, so this is how we evaluate the integral using draws points. We pick a specified number of draws points. We get its coordinates and weights. So we loop over the draws points. Okay, and before we start the loop, we initialize the values to the integral value to 0. We extract the draws point coordinate j and the corresponding weight wt. First we evaluate the function and then we add function multiplied by the weight to the value of the integral. Okay, this is important. We keep on adding. If we don't do this, then we are replacing it, which is not correct. Okay, so we have to add to the previous value. Now finally we can print, and let's see if I run the loop, what happens. I equal to 2. Is this right? Okay, I equal to 2. Okay, so we are using only one draws point. We got the correct value. The reason is this is a linear polynomial. Now for a linear polynomial, that is polynomial of degree 1, we need only one draws point. We can use more. We can verify this using more number of draws points. The result should not change. Okay, for 2 draws points equal to 2. For 3 points equal to 2. For 4 points equal to 2. So we always use the minimum number of draws points, so which is 1. Okay, and similarly we can evaluate the second integral, which is 2 minus 2j plus 3j squared minus 8j cube. This is a cubic polynomial, so we need at least 3 plus 1 by 2. So 4 by 2, 2 draws points. Okay, so here our f is 2 minus 2j plus 3j squared minus 8j cube. So this is our f. We don't need to change anything else. Okay, so everything is same. First let's run this example with one draws point. So with the one draws point we get the integral value as 4, but the integral should be 6 as we said. So to evaluate this integral, 1 point rule is not sufficient. We need at least 2 points. So let's change the number of draws point to 2. Okay, so we get the correct answer. So 6, and we can increase it further to 3 points. The value should not change, and 4 points it should be the same. So this is how we use numerical quadrature to evaluate integrals. Now let's look at another example. Okay, so we have an integral in terms of x, and this is the function. This is the function that we are integrating, and the limits are from -1 to +2, and its value is -6. Now remember, our numerical integration in 1D is always from -1 to +1. Okay? If we have different limits, then we cannot apply this numerical integration rule. This we do not apply this method. Okay, so here the integral is in x, but the numerical integration is in y. Okay, so that's another thing, and we need to apply the change of variables in order to change the limits to from -1 to +1. Okay, so that we can apply the numerical integration, that is the quadrature method. For calculating the integral, we need to change the integral from -1 to +1. In order to do that, we use another variable, which is j, our local variable that we use for the numerical integration. So to do that, first what we do is we apply the change of variables method. like principal. Now, so what we do? So we have the integral in x. So from h1 to h2 to apply the change of variable. So we calculate the limits in terms of xi at h1 and h2, and our f of x we change from x to xi. So instead of x we will have xi's. Since we are using change of variables, we will have some Jacobian. Okay, and then we are evaluating or we are integrating with respect to xi. To apply this change of variable, first we need to express x in terms of xi. Okay, first we need to represent x in terms of xi. So once we know that, we can calculate dx because we need dx. So we can, by applying this kind of chain rule here, so we have dx equal to dx by dy dz multiplied by dz. Now, to express x in terms of xi, so what we can do, we have two limits, right? We have the limits h1 and h2. So we represent x as a linear combination of like our basis functions n1 and n2 and multiplied by h1 and h2. Now once we apply the limits h1, okay, and h2 is 2, and once we simplify we get this expression in terms of xi. So this is x equal to half of 1 plus 3z. From this we can calculate dx by using this formula. So like half is constant, so the derivative of 1 is 0, so derivative of 3 xi is 3, so 3 by 2 dz. So dx is 3 by 2 dz. Okay. From this we can calculate the Jacobian, that is dx by dz as 3 by 2. We know now we have all the pieces to put together the integral to apply the change of variables. Okay, so if we use this expression, that is x equal to half of 1 plus 3 xi, and from this we can calculate xi at h1 and xi at h2. So we get xi equal to minus 1 and xi equal to plus 1 at h1 and h2 respectively. And if we use x equal to this expression in this and simplify, we get 3 xi minus 2, and dx by dz is 3 by 2 and dz. Okay, so we have transformed this integral from variable x into this integral in variable xi. Okay, so now we have the limits from minus 1 to plus 1, so we can apply our numerical integration procedure, and we have xi, this function, as a linear function in terms of xi, so only one gross point is enough. So here our f of x is 3 xi minus 2 multiplied by 3 by 2. Now if we replace, okay, instead of this f, 3 xi minus 2 multiplied by 3 by 2. Okay, so 1 point is sufficient, so I equal to minus 6. I equal to minus 6. Okay, so this is how we apply the numerical integration for integrals which do not have the limits, the appropriate limits. Okay, so we use the change of variables. This becomes important when we want to use the gross quadrature method for evaluating, for calculating the element stiffness matrix, element mass matrix, and element force vector in finite element method. As we have seen here, so in this example, our domain is from 0.1 to 0.3. So because these are the nodes of the element, and these limits are not from minus 1 to plus 1. So this is why we need to apply the change of variable. Okay, So just before going into the element stiffness matrices, so just a, an important concept. Okay, so we have the original integral in x, and this is the modified integral in y. Okay, so in the physical coordinate system, so these are our coordinates x1 and x2, and in y coordinate system, these are our coordinates -1 and +1. No matter what we have in the physical coordinate, the local coordinate in y, we always have the same limits. Okay. Now in this case, the length of the element is 3. Okay, and this element is mapped to this element. Okay, so this point goes to this point, and this point goes to this point, and here, as we can notice, there is a change in length. So originally, in the x coordinate system, the length is 3, whereas in the y coordinate system, the length is 2. Now, this Jacobian 3 by 2, remember this 3 by 2, it tells us the change in length from the physical coordinate system to the local coordinate system. So in the local coordinate system, the length is always 2, and depending upon the values of h1 and h2, the numerator changes. Okay, this represents the change in length. If you look at 2D 3D problems, it represents change in area and change in volume respectively. Okay, now, okay, so this is something I have already covered in essence of FEM video, but if you haven't followed it, so what we do, so we have a physical coordinate system, a global coordinate system, and we map it to the local coordinate system in xi. Okay, and then we approximate the geometry. Here we have only one coordinate, so x. We approximate the geometry using the coordinates of the nodes and the basis functions in the xi coordinate system. Then we have the Jacobian of the mapping. From the Jacobian of the mapping, we can calculate the derivatives of the basis function with respect to physical coordinates. And then from these derivatives, we can evaluate the element stiffness matrix. Okay. So we do that by using the gross quadrature. We have a low power gross points, and then at each point we evaluate G, we evaluate J, and we get the weight. Okay, so the weight factor, and then we keep on adding to the element stiffness matrix. So let's see how this works. Okay, so this is our element stiffness matrix, and note that G is an array. We have two basis functions, so G is dou inverse by dou x and dou into by dou x. So here G is 1 by 2 array. And when we do G transpose, we get 2 by 1 array. So 2 by 1 multiplied by 1 by 2, we get a 2 by 2 matrix. These are our basis functions in 1 and 2 in terms of xi and their derivatives with respect to xi. Okay. Now these are our h1, h2 values, and from this we calculate the element length, and for this problem we assume that mu is 2.5. By using 1-point rule, let's see how we calculate the element stiffness matrix. Okay, so first we evaluate the derivatives of the basis functions with respect to xi. We don't need the basis function themselves for stiffness matrix. Okay, so we evaluate the derivatives of the basis function with respect to xi. They are constant. Okay, so they don't depend on xi. Okay, and then we calculate the Jacobian. Jacobian is dx by dxi. That is, okay, so we multiply the derivatives with respect to the local coordinate xi, and then multiply this derivative with the corresponding nodal coordinate and sum them. Okay, so dou n1 by dou xi multiplied by x1 plus dou n2 by dou xi multiplied by x2. So dou n1 by dou xi is minus half. Okay, minus half. x1 is 0.2. Dou n2 by dou xi is plus half. x2 is 0.3. So this gives us 0.1 by 2. So j is 0.05, and since it is just a scalar, j itself is its Jacobian, and then we can calculate dou n1 by dou x, dou n2 by dou x. Okay, dou n1 by dou x is minus 10, dou n2 by dou x is plus 10, and once we know dou n1 by dou x, dou n2 by dou x, we get g. Okay, and then we can calculate the stiffness matrix. So we remember we are using raw spines, right? So mu g transpose is g is minus 10 plus 10. Okay, g is minus 10 plus 10, and g, this is g transpose. Okay, mu we have mu is 2.5. Okay, and this is the Jacobian, and w is the weight. Okay, once we substitute for mu 2.5 and evaluate everything, we get a 2 by 2 matrix with this coefficient. This is exactly what we calculated using the analytical expression. Okay, so this is correct, and this works fine because the stiffness matrix is constant in terms of J. So here we have mu G transpose G, and G is a function of the derivatives, and the derivatives are constant. Okay, so they are not function of J. That is why the stiffness matrix is constant in terms of J. Since it is a constant, we need only one Ross point for calculating the stiffness matrix accurately. So this is a like constant matrix. So like each entry in the stiffness matrix is constant. So we need only one Ross point to evaluate the integrals. In a similar manner, we can calculate the force vector. For force vector, we need the basis function because here we have n transpose f. Okay, we calculate n1, n2. Okay, n1 is off, n2 is off at j equal to 0. Then dou n1 by, and then the other values for calculating Jacobian. So here our n is, okay, so n is the matrix of n1 and n2, so 0.5, 0.5, n transpose becomes a column matrix, so 0.5, 0.5. Okay, this is our f is 2, this is the Jacobian, and this is the weight. So once we do all the arithmetic, we get this, which is what we had calculated using the analytical expression FHE by 2, 1, 1. Okay, again for constant f, okay, so this force vector is linear in terms of j. Only n1 depends on j, and this n1 and sorry, only n's depend on j. n1 and n2 are linear in j. Okay, sorry, this is plus. So only n1 and n2 are linear. N1 and N2 are linear in j, so we need only one Ross point for evaluating the force vector. Similarly, we can apply. Okay, similarly we can apply the method for the mass matrix. Okay, so mass matrix is given by this. Okay, so here, and this is n transpose n. This is our row j. Then I'm missing a 2 here. Yeah. Okay, so if you do the arithmetic, we get this matrix, but this is incorrect. Our mass matrix should be 0.4, 0.2, 0.2, 0.4. But here we have 0.3 everywhere. This is not correct. The reason is, so n1 and n2 are linear in j. So since we have n transpose n, so when we multiply them, we will have a quadratic function in j. Okay. So the first term would be 1 minus j multiplied by 1 minus j divided by 4. So 1 minus j square, which is quadratic in j. So as we have seen, one Ross point is not enough for evaluating a quadratic polynomial. So we need at least 2 plus 1 by 2. So 3 by 2 is 1.5. We don't have 1.5. So we need at least 2 quadrature points. Now let us implement this in MATLAB. Let us see how we actually implement the calculation of the stiffness matrix. Okay, first. Okay, so I'm using this function, new function, and this part is the same as before. So here for a given number of gross points, I am getting the number of the coordinates of the gross point and the weights. And here these are our nodal coordinates h1, h2. This is the element length. These are our parameters rho, mu, and f. Okay, so we calculate the element stiffness matrix first. So first we need to initialize it. This is a 2 by 2 matrix, and we loop over the gross points 1, 2, n number of gross points. We end it, and after calculation we print it for checking. Okay, so first we get xi, and then our weight at the gross point. Okay, then we calculate the basis functions n1, n2. Okay, n1 is 1 minus xi divided by 2, n2 is 1 plus xi divided by 2. So then we prepare our n array. So this is n1, n2. Okay, we don't need it for the stiffness matrix, but we will calculate it for a future. Okay, and then so dn1 by dxi. Okay, so dn1 by dxi. dn1 by dxi is minus of. Doesn't depend on the coordinate xi. Okay, and similarly dn2 by dxi, which is plus half. Okay, dn2 by dxi is plus half. Now, using this, we now calculate the Jacobian. Jacobian is dn1 by dxi multiplied by h1. Okay, so here. Okay, so this is the next step we are implementing. Okay, so dn1 by dxi h1, dn2 by dxi multiplied by h2. Okay, so now determinant of j. Okay, here Jacobian is just a scalar, so like it doesn't make much sense to do this, but it's an important practice to cultivate to do this, because we need to do this in 2D and 3D problems. Okay, this is our determinant of Jacobian. Okay, so once we know j, we can calculate the derivatives with respect to the physical coordinate x. So dn1 by dx equal to so dn1 by dxi, okay, j inverse multiplied by dn1 by dxi, right? Okay, so j inverse of the Jacobian. Okay, so j inverse multiplied by dn1 by dxi. Similarly, dn2 by dx, j inverse multiplied by dn2 by dxi. And then from this we can prepare our G matrix. Okay, J is dn1 dx, dn2 dx. Remember, here dn1 dx, dn2 dx, not dn1 dxi. Okay, so our G is a matrix of the derivatives of basis function with respect to physical coordinate x, not the local coordinate y. Okay, this is very important. Okay, so we prepare G, and then so we calculate the K. Remember, we need to keep on adding to the previous values. So this is important. We should not replace it. So here we have mu, okay, mu multiplied by G transpose, okay, G transpose multiplied by G, and then multiplied by the determinant of Jacobian and multiplied by the weight. This is how we calculate the element stiffness matrix using the Gauss quadrature. So I have selected one point. Let's see what we get. Okay, so using one point we get the correct value. Okay, so as we have calculated here, 25 minus 25 minus. Okay, if I change the number of points, if I increase it, it shouldn't affect the result unless there is a bug. If I have a bug somewhere, then the result may be different. But if we have no errors in the code, no bugs in the code, then as you increase the number of gross points, the result shouldn't change. The stiffness matrix shouldn't change. Okay, that's for the stiffness matrix. And let's repeat the calculation for the force vector. Okay, the force vector is of size 2 by 1. Okay, so we have already calculated n, so that's why I said it is for the future. Okay, so for the force vector we have F equal to is n transpose multiplied by F multiplied by the determinant of Jacobian multiplied by weight. Okay, so n transpose multiplied by F multiplied by determinant of Jacobian multiplied by weight. Okay, and then let's print Fe. Okay, so Fe is 0.1, 0.1, which is what we know. Okay, again, if we increase the number of gross points to 3, it shouldn't change. So as the last one, we calculate the mass matrix. Okay, mass matrix is of size 2 by 2. Okay, and then it is the same, me equal to me plus. Okay, so for the mass matrix, rho multiplied by n transpose multiplied by n multiplied by det j multiplied by the weight. Okay, so rho multiplied by n transpose multiplied by n multiplied by det j multiplied by weight. Okay, we have, let's start with 1 point. Okay, let's print me. Okay, yeah, so this is what we got. We calculated using 1 point rule. Okay, 0.3, 0.3, 0.3, 0.3. Okay, as we said, 1 point rule is not sufficient for calculating the stiffness mass matrix because it is a mass matrix and each entry of the mass matrix is a quadratic function of xi, so we need at least 2 points. Okay, let's change to 2. Now we have m equal to 0 0.4, 0.2, 0.2, 0.4, okay, which is the correct one. Okay, so we have here for reference 0.4, 0.2, 0.2, 0.4, and it shouldn't change if we increase the number of gross points. Okay, and last one, right. Okay, so this is how we apply the Gauss quadrature method to calculate the element quantities, the stiffness matrix, mass matrix, and force vector. The advantage of doing so is, okay, so you might be asking, okay, we already have the expressions, why not we use the expressions? We can use the expressions if the problem is simple. Okay, if we are solving just this problem, okay, we can use the expression. What if the problem is little bit more complicated. For example, f is no longer a constant. If f is let's say sin x, but if we don't know beforehand. Okay, you want to input a complex like complicated function. Okay, so in that case, instead of taking a constant, so what we can do, if let's say f is a sinusoidal function. Okay, f depends on the coordinate x. Okay, so for this we need to calculate the coordinate. Okay, so which we do it here. So our x is n1 x1 plus n2 x2. Remember, this is the geometry approximation that we start with. Okay, so this is the so we calculate x, and then at this coordinate x we calculate f. Okay, see, now you can check. See, one point rule now is no longer sufficient. When we use one point rule, we get both values as the same. And only when we use 2-point rule, we get different values, and this is the correct. And if we increase it to 4 points, okay, and in this manner, we can change the expression here. And okay, so we change the expression here, and we can calculate the element force vector for arbitrary functions. And another advantage is, suppose you are solving a nonlinear problem. Okay, so in the nonlinear problem, the stiffness matrix is no longer can no longer be represented using the closed form expressions, because the stiffness matrix would itself depends on the solution u. So in that case, we need to apply the numerical integration procedure to calculate the element stiffness matrix and element force vectors and element residual vectors. Okay, and this becomes quite powerful when we go to solving 2D elasticity problems, Navier-Stokes, and 3D problems. Okay, I hope you found it useful. If you have any questions, please post in the comments. Thank you.